Welcome back, everyone. Before the break, we had looked at a sigma example of an infinite series. For the next portion of the lesson, I'm going to look at some other examples about calculating the sum to infinity. Please remember that I can only calculate the sum to infinity when my ratio is between -1 and 1, and when the ratio is not equal to 0. So the ratio has to be a proper fraction in order for me to calculate the sum to infinity. Let's have a look at the next example. So guys, we've been asked to consider the geometric series that goes m minus 5 plus m minus 5 squared plus m minus 5 cubed going on. A is asking me for what values of m is the series convergent. B is asking me to calculate in terms of m the sum to infinity of the series if the series is convergent. And hence, for number C, we need to calculate the sum to infinity of the series 7 minus 5 plus 7 minus 5 squared plus 7 minus 5 cubed. So let's get going with A. So we've been asked to consider the series, and we've been asked for what values of m is this series convergent. Great. Before I even start writing, please just remember that the definition of a convergent series means that the ratio has to be between -1 and 1. So what this means is that I need to first establish what the ratio is in the example behind me. Once I know what that ratio is, I'm going to isolate m in order to determine the values that m can lie between in order for the series to be convergent. So let's write down the next few steps. So, if I'm going to be calculating the common ratio for this example, I need to see what has each term been multiplied by to get to the next term. So I know that I can commonly write the common ratio is equal to term 2 over term 1. Term 2 is equal to m minus 5 squared, and I'm going to put that over m minus 5. Hopefully everyone can see that m minus 5 squared over m minus 5 is equal to m minus 5. So that means for this example, my common ratio is equal to m minus 5. But I know that for the series to be convergent, the ratio has to lie between -1 and 1. So what I'm going to do is I'm going to substitute in my ratio into this middle portion so that I can isolate the values for m that this series will be convergent. So on my next line, I'm going to say that the ratio of m minus 5 has to be between -1 and 1. We want to know for what values of m is this series convergent. So in order to determine the barriers that will work, I'm going to have to add 5 to the left-hand side of the inequality. I'm also going to have to add 5 to the right-hand side of the inequality. So that means that I'm going to have 4, because -1 plus 5 is 4. And then I'm going to have 6. So this statement is saying that m has to be greater than 4 but less than 6. So that means for this series to actually be convergent, m has to be between 4 and 6. That will mean that this sum to infinity can be calculated only if m is between 4 and 6. Cool. Let's have a look at B. We are going to calculate in terms of m the sum to infinity of the series m minus 5 plus m minus 5 squared plus m minus 5 cubed going on. We've been told that we can assume that the series is convergent. Cool, guys. So just a reminder, because the series is convergent, I can calculate the sum to infinity. In order to substitute into the sum to infinity, I need to have my a present as well as my r. I want my sum to infinity in terms of m. So that means whatever our sum to infinity is, we're going to simplify it in terms of m. Let's go back to the board. Great, so I need to substitute in a. A is my first term, and I can see that m minus 5 is my first term. On the previous slide, we discussed that the common ratio is equal to m minus 5. So let's substitute in a and r. So the sum to infinity will be equal to m minus 5 over 1 minus m minus 5. So we're now going to simplify this so I can calculate the sum to infinity in terms of m. So the sum to infinity will be equal to m minus 5 over 1 minus m plus 5. Great. So if I want to conclude, I've got the sum to infinity in terms of m will be equal to m minus 5 over 6 minus m. Great, everyone. I hope that everyone's comfortable so far. This example looks slightly weird because we're used to the sum to infinity actually approaching a specific number. For this example, the sum to infinity is approaching a number, except this number has been represented in terms of m. So it looks a bit different, but we've still calculated the sum to infinity by substituting in our a value as well as our r value and making sure that it has been simplified. So my answer is in terms of m. Let's look at C together. So it says, hence, calculate the sum to infinity of the series 7 minus 5 plus 7 minus 5 squared plus 7 minus 5 cubed. So what I want everyone to do in this example is to try and see the link between what has been presented to you and what was asked. So we know the pattern was given to you as m minus 5 plus m minus 5 squared plus m minus 5 cubed. So I'm hoping that everyone can see the link. And the link is that the m has been replaced with a 7. So we've now seen that there is a connection between C and with what was asked at the beginning. For this example, m is equal to 7, and I've been asked to calculate the sum to infinity. So let's write that down. For this example, m is equal to 7. But there is a problem with m being equal to 7. What could that problem be? I'm going to give you a few seconds to think about it. Have I, in this entire example, and if you've just joined us, we've been working with m throughout this example, I put restrictions on my m value a bit earlier on in this sum. I'm going to go back to the slide where I worked out the values of m that will mean that the series is convergent. So I'm going to go back to that slide, but please keep in the back of your mind, m is equal to 7, and why could it be a problem if m is equal to 7? Let's take a look back at that slide. Cool, so I've asked you guys to keep in the back of your mind that m is equal to 7 and why that is a problem. If I go back to A, I had to determine the values of m for which the series was convergent. We then solved the inequality and saw that for the series to be convergent, m has to be between 4 and 6. So if I go back to C, I know that for this series to be convergent, m has to be between 4 and 6. And why is it important for m to be between 4 and 6? It's important because it will actually mean that this series itself converges, and I'm allowed to calculate the sum to infinity if the series converges. So I cannot calculate the sum to infinity as m is greater than 6. So that completely breaks this condition. So I hope that everyone's comfortable with what I've done. Because m is greater than the values that m is allowed to have, m is only allowed to have a value between 4 and 6, because that means that the series converges, so I can calculate the sum to infinity. Because m is greater than that, I am not allowed to calculate the sum to infinity. Let's have a look at the next example together. Great. So just a reminder that now we are going to be using the formula for the sum to infinity of a geometric series to write down 0,8 recurring as a proper fraction. So first things first, let's write down what 0,8 recurring is. We've discussed that it's going to be 0,88888 going on. This means that I can actually write 0,8 recurring as a sum, because it's going to be 0,8 recurring is equal to 0,8 plus 0,08 plus 0,008 plus 0,0008, going on and on and on. If I want to be able to express the sum to infinity of this number, I need to establish what A is and what R is. I'm just going to have a look, and I can see that if this was a geometric series, 0,8 would be my A value. If I want to actually be able to substitute into the sum to infinity, which we know is equal to A over 1 minus R, what we're going to do is we need to actually see what the value of R is. So from 0,8 to 0,08 to 0,008, I need to establish what my common ratio is. I know that I can work out my common ratio to be term 2 over term 1. Term 2 is equal to 0,08 over term 1, which is 0,8. This is going to give me a common ratio of 0,1. So I can see that I multiply by 0,1 each time. So if I substitute into the sum to infinity formula, A is equal to 0,8. I'm then going to put this over 1 minus my ratio, which is 0,1. Let's put this into my calculator. So I'm going to have 0,8 over 1 minus 0,1. This is going to give me a final answer of 8 over 9. So the sum to infinity for 0,8 recurring can be written as 8 over 9. Wonderful, everyone. So this is not the only case where I can actually use the sum to infinity to write a recurring decimal. The biggest thing is to establish what the A is and what the A would be during the sum, and then to establish the common ratio. Because the decimal is reoccurring, it's going on an infinite basis, which means that I can calculate the sum to infinity. Great, everybody, but I really hope that you've enjoyed today's lesson. We've discussed when a series is converging and how the terms of a convergent series have to be getting closer to 0, and that the series for a convergent series has to be approaching a finite number. We've used the formula for an infinite series to calculate the sum to infinity, And hopefully these examples have helped you. Otherwise, I hope that you have a wonderful day, and I hope to see you again soon.